Good evening, everyone. Welcome you all to the problem solving session. This is the summary session wherein we see everything from week 1 to week 12. That is the session that happened yesterday. So, let us wait 2 more minutes for others to join and then we will start. We will start like by the time we give introduction, people will join. All right. Okay. So this is the problem solving session conducted by myself, Ankara, a research scholar from Department of Chemical Engineering, IIT Hyderabad. So the course is Computational Fluid Dynamics. The course code is MOZ25CH18 and course instructor, as you all know, is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras. So these sessions, the problem solving sessions have been conducted every week wherein we solve the problems related to that week's assignment so that it was helpful for you guys to submit the assignments on time. So today's session we are not going to see any specific problems, rather we are going to see a summary of problems from week 1 to week 12 so that it will be helpful when you submit the assignments. Uh, that assignment of week 12 as well as from exam point of view it will be like a quick revision. That is one thing, and if you have any doubts from the previous sessions you can ask in today's session also, so that we can solve the doubts from week 1 to 12 if you have any. And yeah, I have chosen a set of problems, 12 problems, one from each week. So if you have anything in your mind, we can do it as well. So yeah, let us now start. So basically, we are just to give you a quick layout. So this computational fluid dynamics course is a 12 weeks course, and we have seen or covered from basics to advanced. Just So in the week 1, what we have seen about the calculation of flow in a rectangular duct. So we had seen about the introduction to the problem solving by using the finite difference approach. And week 2, it was about flow through a triangular duct. So since it was a triangular duct, we also saw how to solve problems using finite volume method and what are all the basics. Even though we didn't go in depth into it, we have seen about the basics of how the equations will be arising from those methods. And when we talk about CFD, the main thing is we are solving equations uh, that are governing the fluid flow. In basic flow systems, we will be solving continuity equations and momentum conservation equations. In addition, if we are experiencing any heat transfer problems or any mass transfer also taking place, we will be solving additional equations for those as well. So in week 3, we have seen about the derivation of equations governing the fluid flow of for the, like continuity equation and the momentum conservation equations, because those are the basics of which our CFD is entirely based upon, and or any fluid dynamics problem is based upon. And week 4, it is about equations for incompressible flow and boundary conditions. When we talk about CFD, we are solving equations, but we need to know certain values beforehand. So consider the problem of what do we say, or any fluidized bed. So here we need to know the inlet velocity, that is the fluid inlet velocity, or a basic application like a flow of water in a pipe. We are giving it at a certain velocity, the inlet velocity. So that is one boundary condition. And the other outlet, if it is open to atmosphere, we give pressure outlet, and walls we give no slip boundary condition. So these are certain criteria or certain boundary conditions which we need to apply so that we will be able to solve for that system of equations. So in week 4, it is equations for incompressible flow and boundary conditions associated with it. And there are various types of boundary conditions like Dirichlet boundary condition and Newman boundary condition. In Dirichlet boundary condition, what we do is that we give a value to the variable. For example, in our case of water flow in a pipe, we are giving value of the velocity. So that is Dirichlet boundary condition. On the other hand, we have Newman boundary condition. Newman boundary condition is nothing but here we are specifying the value to the derivative of the variable. For example, in adiabatic boundary conditions, what do we say? We say there is no mass transfer. So the derivative of a mass variable will be 0. So certain like, I mean, it won't be 0, but it will be like certain constants. So these are the things which we specify across the boundaries. We will be able to know which type of flow or things are happening inside the system, and accordingly we will give boundary conditions. In certain cases, we will be giving a combination of Newman and Dirichlet boundary conditions as well, or we will be giving Newman at one end and Dirichlet at other end. So all those things are possible, so which we have seen in week 4. And in week 5, we have seen about the finite difference approximations. Finite difference methods we are getting from the Taylor series approximations, and there are various concepts involved again, which are forward difference, backward difference, central difference. So those things we have seen in depth in those things. And week 6, it is about basic concepts of CFD. For example, when we are talking about CFD problems, we are we know that we need to solve the system of equations, but one question remains is that whether we will be getting the proper solution, or whether we will be getting the converged solutions. In most of the cases, if we are not specifying proper conditions, the chances of divergence are very high. So based on the numerical problem in our hand, we need to ensure two things, that is consistency and stability, so that we will be getting converged solutions. That is what is accounted through Lax equivalence theorem as well. So those things we have seen. And in week 7, it is about solution of Navier-Stokes equations for compressible flows. So we have compressible flows and incompressible flows based on the Mach number. And for compressible flows, what happens is that density is varying. So we are not taking it out as a constant in the continuity equation. It remains in the continuity equation. So we have methods like beam warming scheme, artificial compress sorry, not artificial, beam warming scheme and McCormick scheme. Those schemes are specifically designed to get the solution of Navier-Stokes equations for compressible flows. And in week 8, it is about solution of Navier-Stokes equation for incompressible flows. When we are talking about incompressible flows, the situation arises where density is no longer varying, it is constant. So what we need to do, we need to take it out as a constant in the continuity equation. So in the continuity equation, the density term is absent, whereas in the momentum conservation equation, density term is present. So it is no longer we are not able to decouple it, like we are not able to solve it similar to how we did for compressible flows. So there are various other techniques. One is artificial compressibility approach. In artificial compressibility approach, what we are doing is we are introducing a new term similar to the density factor, and this term we are calling it as compressibility factor, artificial compressibility factor, and we are solving it similar to how we did for the compressible flow systems. And other methods involved are stream function vorticity approach, and other things are pressure correction method. So there are various techniques proposed in the literature which are used for solving Navier-Stokes equations for incompressible flow systems. Most of the things we see in the industries will be like water associated systems. So those in those areas we will have to take other methods into considerations. So till now we have seen about CFD. So as I mentioned, what we do, we have to solve for the system of equations in that system, in that geometry. So first, if we go about a methodology, right, we will see more in depth in the coming up slides, but we divide the geometry into smaller segments, and in each segments we will be solving for the equation. That is how we go about. But what techniques we use, we cannot, those all these are partial differential equations, so we are not able to give the analytical solutions. So we need to go for the numerical solutions. So in the week 9, first we have seen about the basic methods available for getting the solution of linear algebraic equations. Because the partial differential equation, through discretization, we are converting it into linear algebraic equations. And we have seen about the basic methods. So basic methods involved are like Gauss-Seidel approach and Jacobian approach, and like basic numerical methods available for the solution, which we all are very familiar. And week 10, it is about same solution of linear algebraic equations, but we have now advanced to the advanced methods. Advanced methods include successive over relaxation techniques, alternating direction implicit, in which each direction we solve implicit, keeping the other directions explicit. So those are all the things which we have seen, even though uh, you might not be required to apply everything in your applications. Knowing is better, because we will be learning to appreciate certain things after we know a lot of things. And like these are all the techniques proposed in the literature. So once we get to know so many advancements made in CFD, we will be like appreciating things better. So that is week 10, and in last week we have seen about basics of finite volume method, including grid generation. Grid generation, we have seen two techniques. One is structured grid approach and the other is unstructured grid approach. So in structured grid, it was easier to get the solution, whereas in unstructured grid it was easier to mesh the geometry, that is complex geometries. In structured grid, you need to be consciously aware of changing the grid density at one position when you are changing it in other position. Like the change in one position will indirectly affect the other position also, which you need not worry when you're talking about unstructured grids. So there are pros and cons of each techniques. It finally comes to what is your requirement and what you're willing to sacrifice. So those things matter. And grid generation and finite volume method. And in last week, that is 12th week, we have seen about turbulence flows and turbulence modeling. which we have seen actually in yesterday's class from 3 p.m. to 5 p.m. It was about turbulent flows and turbulence modeling. When Reynolds number is greater than certain value, critical value, we call the flow as turbulence, and we will be encountering certain difficulties during the solution of the problem. So there are various techniques proposed, including Reynolds average, Navier-Stokes equation, and so on. Like those things come into picture, and otherwise those things have use certain closure techniques. If you do not want closure techniques, you need to go with the direct numerical simulation, which is again computationally very expensive. So again, like it depends on what is our ultimate requirement and what we are willing to sacrifice for. So this is the course layout for the 12 weeks course, and the course theory is laid out by the professor, and each has been divided into modules, and all the videos are given in the NPTEL. Also the problem solving session for each week we had one session, and those videos are available. The link for the videos are available to you as well in the NPTEL. So that's it for 12 weeks. Like to give you an idea of what we have seen. By now, we are all very familiar with what we have seen, and most of you would be appearing for exams. So, if you have any doubts or any specific topics which you want to be discussed today, we can do it. And for books and references, we have 5 books and references. First one is Verziger, J.H. and Perick M 1999, Computational Methods for Fluid Dynamics, Springer, Berlin, Germany. Second one is Hirsch C 1988, Numerical Computation of Internal and External Flows, John Wiley and Sons, New York, USA. And in third one it is Patankar SP 1980, Numerical Heat Transfer and Fluid Flow, Hemisphere, Washington DC, USA. So finally we have seen about Versteeg and HK, Malalsekara W 1995, and Introduction to Computational Fluid Dynamics, the Fluid Volume Method, Longman Scientific and Technical, Harlow, Essex, UK. And finally it is Anderson JD 1995, Computational Fluid Dynamics, the Basics with Applications, McGraw-Hill. So these are the 5 books which we have used for the course. I hope most of you would have read about it at some point, read through the books at some point. So that's it for books and references. So yeah, and like if you have any feedbacks for me as well, you can share it with me, or yeah, you can share it with me. And feedback links are provided by NPTEL as well. So if you can do it, it is well and good. I'll be happy to take feedbacks, or if you are willing to tell me now in the session, that is also fine. So now we will move to the session. So now we are having problems of one problem from each week. So we have 12 week and 12 problems. So that is what we are going to see in today's class. Before that, we will just quickly go through what is CFD, and although we have seen, it might be repetitive for few, and if you haven't attended the before classes, just to give you an idea of whole CFD things covered. So what is CFD? So the figure will give you an idea. In the 17th century, there was experimental fluid dynamics very well understood and very well practiced. Like for all the problems, we had experimental fluid dynamics. So we need to perform lots of experiments which gave you a solution to what we are looking for. But when we talk about experimental fluid dynamics, it is very time consuming process, one thing, and it involves a lot of tedious work, and it involves a lot of manpower, it involves a lot of other things, and you need to maintain the external atmosphere perfectly to get the perfect results, which is not always very feasible. So in the 17th century, experimental fluid dynamics was very prevalent, and we got so many findings from there as well. But with a lot of difficulties. People were doing a lot of things, and lot of research works were developed, which again led to theoretical fluid dynamics in the 18th and 19th centuries, wherein we have developed theories behind the fluid dynamics, and equations were written, and all those things happened. And again, like, we are not able to get the analytical solution for all the problems in our hand. So computational fluid dynamics came in the 20th century, wherein you are proposing the equivalent numerical problems and numerical methods to solve the problems in question, which again made a lot of things easier. One is, you need not wait for the perfect um, condition, experimental condition, and fabrication of large experimental setup is no longer required. You can do it with the system, like. But again, the computational resources have very much advanced in the last century. So in today's world, everything is feasible. Like in few decades back, it was a question how we will be able to solve the problems with the computational resources available, because so many CFD problems will be consuming a lot of resources, which is possible in today's world but was not possible in last century also. I mean, like in few decades back, it was bit tricky. But now, with the advanced resources available in our hands, we will be able to do it perfectly. So, what is CFD? As I mentioned, it cannot stand alone. CFD alone cannot stand without the inputs from the theoretical fluid dynamics and experimental fluid dynamics. Although we are able to get our what do we call? Although we are able to get the results through CFD, it would not be meaningful if you cannot compare it with theoretical or experimental results. Otherwise, CFD would simply be like interpretation from the CFD will not be very meaningful when you blindly go with CFD alone. So we need inputs from theoretical fluid dynamics, and we need inputs from experimental fluid dynamics also to get the CFD accomplished. Similarly, theoretical fluid dynamics alone will not be sufficient. You require things from experiments and CFD. Computational experiments. Similarly, experimental fluid dynamics alone cannot stand. We need theory and computational resources as well. Because one cannot stand alone, we need support from the others. For example, when you are talking about fluidized beds or any complex systems involved, you need experimental results to validate your models. Like, without validation, the models are not meaningful. We cannot say for sure whether the model is performing correctly. So for that, we need experimental results as well. So everything stands hand in hand. And coming to CFD, what it comprises of. So, as we all know, we are solving a problems numerically, so mathematics is involved, and we are solving for the engineering fluid dynamics application, so again it is involved, and we are using computational resource, so computer science is also involved. So it is like a involvement from all the domains. Mathematical domain is involved, computer science domain is involved, engineering fluid dynamics is involved. So computational fluid dynamics is a in is I mean it is standing with the involvement from various domains. So that is this. And what we do in CFD, if we divide it into three categories, first one is pre-processing, second one is solving, third one is post-processing. What we do in pre-processing, we have one system in our hand, and for example, let us take our classical example of water flow in a pipe. So that pipe, we are dividing it. That pipe, we need to know the geometry, like its dimensions and geometry we need to have. So from after geometry creation, we will go for meshing. Meshing in the sense, we will divide the geometry into smaller segments. So that happens in pre-processing, wherein we create the domain, we mesh the domain, that is in covered in the pre-processing thing. Next one we have solving. So after pre-meshing, we will be having smaller sized cells. In each of those cells, we will be required to solve for the Navier-Stokes equations, or the equations in our hand, which may involve continuity, which will involve continuity and momentum conservation equations. But if the problem under our consideration is involving heat transfer applications also, those additional equations will also be coming into picture. So we will be solving for the equations, and we will be getting variables like pressure, velocity, and if temperature is involved, those things also. So we will be solving and getting those results. And next comes the post processing. So once we get the values, we should convert it into meaningful results. We will be putting plots, we will be putting contours, we will be getting plots and so many things, so that we will get to know how meaningful our results are. So that is what happens in CFD, like pre-processing, solving and post-processing. So that is the thing in CFD. Now like equations governing fluid flow. So till now we have seen equations governing fluid flow, continuity equations and momentum conservation equations for basic CFD applications. I'm not talking about heat transfer and mass transfer problems here. So we need to know what those equations are. This is generic equations. So first one we have is continuity equation, and it is nothing but it is for the incompressible flow systems. For incompressible flows. So it is dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0 for incompressible flows. And momentum conservation equations we have in three directions, x, y and z. So first one, it is in x direction, it is rho into dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z equal to minus dou p by dou x plus rho gx plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. So this is for the x direction momentum conservation equation. Next we have y direction momentum conservation equation, which is as this: rho into dou v by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z equal to minus dou p by dou y plus rho gy plus mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. And finally z direction momentum conservation equations, which appears as this: rho into dou w by dou t plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus dou p by dou z plus rho gz plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So here u is the x component velocity, v is the y component velocity and w is the z component velocity. So three momentum conservation equations we need to solve, and this is for basic flow systems. We are not considering the equations for heat transfer and mass transfer applications here. Energy conservation equation also comes into picture, and species conservation equation also comes into picture when we are dealing with those applications. So I hope you are clear with this. So now we will move to problems. Oh, okay. Before that, just momentum conservation equations in generic form without I mean, we are not writing it in terms of three directions. Rather, we are giving us whole equations just to see what are all the terms signifying. So we can write it as rho into dv by dt equal to minus del p plus rho g plus mu del square v. So here we are having four terms. What are all these terms representing? First one is given by total derivative. We call it as total derivative. and this is pressure gradient, momentum conservation due to pressure gradient, and this is momentum conservation arising from the body forces, and last it is momentum conservation arising from the diffusion term. So this total derivative actually is a comprising of rho into dou v by dou t plus v dot del v. So here it is change of velocity with time, and here it is change of thing with convection term. Due to convective motion, this momentum change is arising, and this is due to diffusion, and this is due to pressure variation, and this is due to body force variation. So these are all the things behind the momentum conservation equation. So yeah, now we will move to problems. These problems are one problem from each week. So the first question is actually, in a laminar fully developed flow through a pipe. In a laminar fully developed flow through a pipe, option A, axial pressure variation is linear. Option B, radial pressure profile is linear. Option C, radial pressure profile is parabolic. Option D, pressure is constant. So since we all know the answer to all of these problems we have discussed in that particular week, so I'll just give you a minute time. Also here the answer is next to the problem itself. The figure clearly explains the answer. So I'm giving you a minute time so we can discuss it. Okay. So here this is velocity variation in a laminar fully developed flow through a pipe, and this profile shows us the pressure variation in a laminar fully developed flow through a pipe. So as we are able to see, this is the developing region and this is the fully developed region. This is again developing region, this is fully developed region. So this is velocity variation and this is pressure variation. So in the in the developing region, we are not able to see any pattern, even though it is variation is there, but we are not able to see any particular relation. But here in the fully developed region, what are we seeing? We are seeing a linear pressure drop in fully developed flow region. So linear pressure drop in a fully developed flow region. So axial pressure variation is linear is the right answer. Option A is the right answer. Axial pressure variation is linear. So answer to question 1 is, in a laminar fully developed flow through a pipe, axial pressure variation is linear. So now we will go to question 2. In question 2, we are now dealing with this particular figure 2, wherein as we know that in week 2 we saw about the flow through a triangular duct. So what is asked in the question? You wish to find the velocity in the starred cell in figure 2. So this is figure 2. How many algebraic equations do you have to solve? So you wish to find the velocity in the starred cell in figure 2. How many algebraic equations do you have to solve? Options are option A 1, option B 4, option C 6, option D 10. So again take a minute and we will discuss the answer. Alright. So now since it is a triangular flow problem, what we will be doing, we will be solving equations in each of the cells. So we need to count a number of cells. So I mean only then we will be able to get the all the correct answers. So here it is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So we have till 10 cells. So the answer is option D. 10 is the right answer. So in looking more in detail in this problem, we have a direction cosines nx and ny which are acting outward normal for each cells. So since it is like here we are talking about outward normal for each side since it is a 2D problem, and gradients are evaluated at midpoints of each side using value of the cells and those of the neighboring cells are boundary conditions. So here this is how we go in the finite volume approach. So it is we are integrating over each cell n dot del w into dl. So here n is the direction cosine and del w is the gradient, velocity gradient, and dl is the length. So for our case it will become like summation over each cell n dot del w and into L equal to CAI. So C is some constant, A is the area of the cell. So for our case it becomes like for each triangle we are solving it. So nx into dou w by dou x plus ny into dou w by dou y over AB into length of AB, that is side AB and into length of AB. So for each triangle we are talking about, plus nx into dou w by dou x plus ny into dou w by dou y into at BC into length of BC plus nx into dou w by dou x plus ny into dou w by dou y over CA into length of CA equal to C into area of ABC, that is area of triangle with A, B, C and vertex points. And so figure 2 contains 10 cells resulting in 10 algebraic equations and 10 unknown velocity for each cell. So we need to solve all of them simultaneously to get the value of velocity in that particular cell. Even though we are talking about a single cell, single velocity, velocity at a single cell, we need to solve all cells resulting in having all 10 algebraic equations so that we will be getting the value, velocity value for that particular cell in question. So that is how we go about doing it. So this is question 2. If you have any questions at any point of time, you can stop me. So now we will go to question 3. So in question 3 we have this particular figure wherein flow is with inlet velocity V in, and we have four planes A, B, C and D. A is the inlet plane, D is the outlet plane and B is almost at the center and C is closer to the outlet plane. So with reference to the given figure, if W is 0.04, H is 0.024 and L is 1.5 meter. So we are given dimensions of W, H and L. So let us keep W is this, H is this and length is this. Inlet velocity of air whose density is 1.2 kg per meter cube and viscosity is 1.8 into 10 power minus 5 kg per meter second. Inlet velocity of air for an inlet Reynolds number of 1000 would be about dash. So option A it is 0.47 meter per second, option B 0.5 meter per second, option C it is 0.94 meter per second, option D it is 2 meter per second. So this is similar to the question we have seen in last class, that is week 12 class, that is yesterday. So I hope everyone remembers it and you'll be able to do it. So just take a minute and get me the right answer. Okay, we'll see the answer. So, not answers, it is answer. Okay. So, the answer is actually 0.5 meter per second. So, how we will solve the system? First, we will know what is asked. We are asked to find the inlet velocity and we are given Reynolds number. So Reynolds number formula is rho v d by mu. So if we need to know v, we need to know Reynolds number, density, viscosity and diameter of the geometry. So we know inlet Reynolds number, we know the density, we know the viscosity of air. Now one thing remaining is diameter of the column. So since it is a square rectangular duct, so we need to know what is the diameter. So we need to know the hydraulic diameter. So hydraulic diameter is given by 4 times the cross-sectional area of the pipe divided by the wetted perimeter. So we will see the solution. So first, if W is 0.04, H is 0.024 and length is 1.5 meter, inlet velocity of an for an inlet Reynolds number of 1000 would be about dash. Okay, we will write it in a more meaningful way. What did happen? H is point, length is 0.15 meter and inlet Reynolds number is 1000. All right. Okay. W is 0.04, H is 0.024, L is 1.5 meter and inlet Reynolds number is 1000 and Reynolds number is given by rho v dH by mu and dH is given by 4 into WH divided by 2 times of W plus H. So we can give it like 4 into cross-sectional area divided by wetted perimeter. Makes sense, right? So 4 into cross-sectional area divided by wetted perimeter. So 4 into W into H, that is the cross-sectional area of the square section. So it is 0.04 into 0.024 divided by wetted perimeter is again that perimeter of the square section, that is, sorry, not rectangular section. So it is 2 times of W plus H, that is the perimeter of the rectangle. So 2 times of W plus H. So it is 2 into 0.04 into 0.024 divided by 0.04 plus 0.024. So 4 and 2 get 4 divided by 2 becomes 2 and answer is 0.03. So now we know the hydraulic diameter of the pipe as 0.03 meter. Now we need to substitute in the Reynolds number formula. So Reynolds number 1000 equal to 1.2, that is density of air into V into dH is 0.03 divided by mu, that is 0.000018, 1.8 into 10 power minus 5. So we are substituting everything and we are getting the value of V as 0.5 meter per second. So how it is, like 1.2 into 3 roughly gives 3.6 and it is 0.03, so it will be like 0.0036 and divided by 0.0036. Okay, divided by this will give us 1 by 2 1 by 2 1 0.036 divided by 0.0018. So it will give I mean, if you do calculation it will come out 1 by 2 here, I mean 2, it will come this side, 2 into some 10 power minus something, sorry, 2 into 10 power something, because denominator has a smallest number, and if that goes the other side you will get it as 0.5 meter per second. So velocity, inlet velocity is 0.5 meter per second. So that is what we have seen in the question as well. Answer is option B is the right answer. Okay, all right. Same problem we have seen in yesterday's class as well. So I am hoping you are clear with this. So now we will move to next question, that is question 4. In question 4, what is given? Which of the following is already included in the energy equation that we solve along with Navier-Stokes equation for flows with heat transfer and therefore do not require further modeling? So we have seen about energy equation, energy conservation equation also need to be included when we are solving for the heat transfer applications. So in this question, what is asked is that which of the following is already included in the energy equation that we solve with the Navier-Stokes equation, that is in the energy conservation equation for flows with heat transfer. So we do not require further modeling for that. So the first one is conduction heat transfer, second one is convective heat transfer, and third one is radiative heat transfer. So we will see which of the following is already included in the energy equations and we need not do further modeling for that. Options are option A 1 only, option B 1 and 2 only, option C 1, 2 and 3, option D none of the 3. So again I hope you all know the answer to this question, but for our sake we will just look at it and just take a half a minute time and see. Okay, the answer is option B. 1 and 2 only is the right answer. Because in the energy conservation equation we are having convective heat transfer and the conductive heat transfer. So when we look at the heat transfer equation under our question, advective terms includes velocity and therefore takes care of the convective heat transfer. Constant property form for the energy conservation equation is as follows. So it is rho into Cp dot T by dot T plus rho Cp del dot ut equal to K into del square T plus mu into phi b. So this is the energy conservation equation. So here we are having K, that is uh, conductive heat transfer coefficient, and we have advective term which gives us convective motion, convective heat transfer due to convective motion. So both of them are included, that is convective heat transfer is included and conductive heat transfer is included. Whereas if we want to model for the radiative heat transfer, we need to solve for additional equations and we need to solve it by some other means. We need to include equations for those. So that is why we are not including radiative heat transfer. So the equation already includes conductive and convective heat transfer in it. So that is the question. Now we will go to question 5. In question 5, it is about this figure 2. Which of the following statements is false about the discretized equation having the computational molecule shown in figure 2? So we are having the computational molecule in figure 2, which is looking like this, and we are given few statements and we are asked to identify which of the following statements are false. First one, algebraic equation will have at most 5 variable values. Second one, algebraic equation will at least have 5 variable values. And option 3, the coefficient of the variable value at I comma j will be at least equal to the sum of the magnitudes of the coefficients of the other variable values. That is, the coefficient of the variable value at I comma j, if it is at this point, will be at least equal to the sum of magnitudes of the coefficient of the other variable values. So we are given 3 statements and we are asked to identify which of it is false. So options are option A 1 only, option B 1 and 2, option C 2 and 3, option D 1, 2 and 3. So it is very simple actually, but I hope you know the answer. If you want, you take some time and just you just take a paper and write out the answers so we can verify when we discuss the answer in some time. So the answer is option C, that is 2 and 3 is the right answer. Because we will be for this computational molecule, whenever we write the equations, we will be involving 1, 2, 3, 4, 5. Alright, so it will have 5 variables, but that variable will not be the sum of magnitudes of the coefficients of the other variables because it simply cannot be. And second thing, it will have at least 5 variables is wrong, because if imagine if this is falling with the boundary, we will know the value directly, so we need not use a variable anymore. So that time it will become 4. Similarly, if it is falling in the boundary, it will again be 1 less. So similarly, it will, therefore it will not be at least 5, it will be maximum 5. So therefore at most 5 variable values it will have. So first one is true, whereas second one is false and third one is false as well, because it will have at most 5 variable values and that will not be equal to some of the other magnitudes of the coefficients of the other variable values. So 2 and 3 are false. So that is it for question 5. Now we will see question 6. Which of the following is false about Courant number? Options are: Courant number is a condition on the stability of a numerical scheme. High value of Courant number is desirable for consistency. Third one, Courant number condition does not arise for elliptic problems. So these are the 3 statements given and we need to identify which of the following is false. First one, options are option A 1 only, option B 2 only, option C 3 only, option D 1 and 3. So just think about it, we will answer it shortly. Okay, the answer is, we will discuss one statements. Courant number is a condition on the stability of a numerical scheme. So this is true because Courant number basically tells us how much information is passed across the each grids with respect to specific time step. So Courant number is a condition on the stability of a numerical scheme. That is true because it gives a value beyond which the system will become unstable and it will diverge. So it is true. Second one, high value of Courant number is desirable for consistency. One thing, Quran number value is actually dependent on the system applications. So we cannot generalize the value of Quran number, that is one thing. And second thing, we require a lower value of Quran number in most cases. So we have a critical value exceeding which the system will become inconsistent, it will become unstable, it will become diverging. So second one is a false statement. Third one, Quran number condition does not arise for elliptic problems. This is true because in Quran number what it means, it is dependent on grid sizing and time stepping. Elliptic problems are time independent problems. So Quran number condition does not arise for elliptic problems. So that is true. So answer is third one is true. Second one is the only false statement. We are asked to identify which of the following is false. So option 2 is statement 2 is the false statement, which is given by option B. That is 2 only is the right answer. Now options answer is option B, 2 only. So just to give you an quick explanation, what is Quran number? Quran number shows how much information travels across the computational grid in time. It depends on dt and dx. For elliptic problems, elliptic equations are given by del square u equal to 0. And it is in expanded form, it looks something like dou square u by dou x square plus dou square u by dou y square equal to 0. Here it is dou x where spatial variation is there, but time variation is not there. These problems are independent of time. Solution is independent or time independent. So Quran number is not applicable for the elliptic problems. Basically it looks something like v into delta t by delta x should be less than 0.5 in some generic case. So it is v into delta t by delta x. V is the speed with which information is traveling, and delta t is the information traveling time step, and divided by delta x with what grid spacing. So if it is if Quran number is given as v into delta t by delta x, I am not talking about value. Actually the formula varies for different things, but in general case, if it is like this, what happens? V into delta t by delta x if Quran number is given by this. So it depends on equations. For each equation derivation is different. So but for now we are considering v into delta t by delta x. So if it should be less than 0.5. So if it is less than 0.5, the velocity with which information is traveling will be sufficient if it is less than 0.5. Otherwise, what happens if delta x is large and like time step also large, the Quran number will increase. If all those things we need to consider when we are talking about Quran number. So Quran number is time independent. Solution is time independent for elliptic equations. So Quran number is not applicable. And what are the statements was given? Quran number is high value of Quran number is not desired. It is desired to have low value of Quran number, and it is conditional on the stability of numerical scheme. So this is true, this is false, and this is true. So second one is the only false statement. B, 2 only is the right answer. So now we will go to question 7. In question 7, what is asked? Which of the following can be considered as compressible flows? Which of the following can be considered as compressible flows? First one, a racing car traveling at a top speed of 380 km per hour. Second one, a passenger traveling at a bus speed of 100 km per hour. Options are option A, 1 only, option B, 2 only, option C, 1 and 2, option D, neither 1 nor 2. So we are given two cases. In the first, a racing car is traveling at a speed of 380 km per hour, and in the second, a passenger is traveling inside the bus at a speed of 100 km per hour. We are asked to identify which of the following can be considered as compressible flows. So two things. Here compressibility is not a fluid factor, rather it is a fluid property, it is a flow property. Compressible flows, compressible not, it is not asked for compressible fluid. So here it is asked for compressible flows. First thing we need to be clear of that. Second, how we determine it by using Mach number. So Mach number gives us whether the flow we are talking about is compressible or incompressible. So that is the clue I am giving. And time now is 7:03 actually. So let us take a 5 minutes break. In the meantime, you can solve and get the solution for it, and I'll come back. All right. Answer is actually option A. One only is the right answer. We will see how in the next slide. So as I mentioned, compressibility here is a flow property. So we need to identify the Mach number. Mach number is given by m, which is equal to u by c. So it is the ratio of local flow velocity to the speed of sound in the medium. So m is given by u by c. So u is the local flow velocity, c is the speed of sound in the medium. So for air, c is 343 meter per second. So our first case is racing car traveling at a speed of 380 km per hour. So u is 380 km per hour. So we are converting it into meter per second. So we are multiplying by 3000 dividing by 3600, which is giving us 105.56 meter per second. So we are now dividing it by 343. So we are getting 0.343, which is greater than 0.3. Flows are treated as being compressible when Mach number is greater than 0.3. So if it is greater than 0.3, what it means, we are traveling at that high velocity. So it is almost becoming compressible. So that is the meaning. When flows are treated as compressible, when Mach number is greater than 0.3, it means that we are traveling at a very high speed, that the flow can be considered as compressible. So this is first flow is therefore compressible. So the racing car flow is considered as compressible flow. Second one, it is passenger traveling in a bus at a speed of 300 km per hour. So again we are converting u into meter per second, which we are getting as 27.78, and m we are calculating it as 27.78 divided by 343. So we are getting 0.08. So we are calling it as incompressible flow because Mach number is less than 0.3 for this particular flow. So that is the thing. Mach number we are calculating, and for the first case we are getting 0.343 Mach number, so we are calling it as a compressible flow. In the second case we are getting Mach number as 0.08, so we are calling it as incompressible flow. So that is the thing. So now we are going to flows are treated as being compressible when Mach number is greater than 0.3. Now we will go to question 8. Question 8, we are dealing with this particular figure wherein we are seeing incompressible flow through a contraction in a pipe of circular cross section. In a contraction in a pipe of circular cross section. If the flow in figure 8.1 is unsteady, axisymmetric and viscous, then how many partial differential equations need to be solved to get the flow field? Options are 5, option A 5, option B 4, option C 3, option D 2. So almost we know the answer. So just write it down, the answer, we will discuss. Okay, so here when we talk about incompressible flows, we will be solving for continuity equation and momentum conservation equations. So if it is compressible flow, we need to solve for energy conservation equation as well. So since it is incompressible equations, we will be it will be sufficient if we solve continuity equation and momentum conservation equations. So we are not solving any energy conservation equations because there is no heat transfer involved in this case. So first thing is, it is unsteady, axisymmetric and viscous. Axisymmetric. So instead of solving for three momentum conservation equations in the three directions, since it is an axisymmetric problem, we can leave out one direction. So it will be one continuity equation and two momentum conservation equations. So answer is option C, that is 3 is the right answer. Option C, 3 is the right answer. Yeah. As you all know, it is one continuity equation and two momentum conservation equations because it is an axisymmetric and axisymmetric problem. So that is for question 8. Now we will move to question 9. In question 9, it is an interesting problem. So which of the following is or are true about matrix A? Okay. Just a minute. There is some question. So there is something missing here. I will add it. All right. You wish to solve the Laplace equation in three-dimensional domain spanning a length L in the x direction with W in the y direction and height h in the z direction. You have divided the length L into 40 equal intervals with W into 30 equal intervals and height h into 25 equal intervals. You have Dirichlet boundary conditions on all sides. You discretize the Laplace equation using central difference approximation. You wish to solve the resulting set of linear algebraic equations which you have expressed in matrix form as Ax is equal to Q with lexicographic ordering of equations. For this problem, answer the following question. It should be question. Right? So the equation is Laplace equation. So it is del square phi equal to 0. So Laplace equation, it is del square phi equal to 0. If it is Poisson equation, you will be having some function on the right hand side. So we will read the question one more time. You wish to solve the Laplace equation in a three-dimensional domain spanning length L with W and height h. So it is L in the x direction, W in the y direction and h in the z direction. So let us consider some square domain or something like that. Sorry, cube or cuboid something. Alright. And we are dividing the L into 40 equal intervals. X direction, it is 40 intervals. W direction, it is 30 intervals and height h in the 25 intervals. Alright, x is 40, y is 30 and z is 25 equal intervals. You have Dirichlet boundary conditions on all sides. The boundary condition is Dirichlet wherein we are specifying the value to the variable and we discretize the Laplace equation using the central difference scheme. So this is our Laplace equation in 3 dimension. Del square phi equal to 0 and del square phi is dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square equal to 0. So since we are dealing with a three-dimensional domain, we have three dimensions in the equation. If it is two dimension, you need to reduce one and solve accordingly. You have a Dirichlet boundary condition on all sides. You discretize the Laplace equation using central difference approximation. You wish to solve the resulting set of linear algebraic equations which you have expressed in the matrix form as Ax is equal to Q. So after writing the equations, we will be writing it for all cells and we will be end up with so many equations which we are expressing in the form of Ax is equal to q, and A is the coefficient matrix, X is the variables, and Q is the RHS matrix. So for this problem, we need to answer the next question. So in question 9, which of the following are true about matrix A? So first one, it will have 9 non-zero diagonals. Second one, more than 99.9% of elements of A will be 0. And third one, it will satisfy the condition for strong form of diagonal dominance. So options are option A 1, option B 2, option C 3, option D all. So just to give you an idea, since we are having a three-dimensional domain, let us consider it something like this. Each cell, we call it cell, and this space, and this is boundary face, because at the boundaries and each edge, this is edge and this is nodes, which you are able to understand by looking at it. So now we need to identify which of the following is true about matrix A. So yeah, just look at it, we will see the answer. So yeah, answer is actually option B 2. That is the right answer. We will see why. Okay. So the total number of grid points. So if we talk about the cells, right, we have divided into 3 in the x direction. Let us consider in this x direction. Total number of points will be 1, 2, 3, 4. That is nodes grid points will be 4. And we will be having 2 in the boundaries. So it will be 4 total minus 2 interior points. That is how we do the calculation, right? So 3 divisions, we will be end up with 4 points. So 3 plus 1, 4. So total grid points is 40 in the x, 30 in the y, 25 in the z. So 40 plus 1, 30 plus 1 and 25 plus 1. So total number of grid points is 41 into 31 into 26, which is giving us 33,046. So that is the total grid points. So number of equations. So for each grid points in the interior, we will be writing the equations. So as I mentioned, it is in the previous example, if we have seen, it is 3 plus 1 minus 2 or 3 minus 1 number of interior grid points. So again here we are doing 40 minus 1 interior grid points. So that number of equations we will be writing. 40 minus 1, 30 minus 1 into 25 minus 1. So we are having 27,144. And the Laplace equation is given by dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square. So when we do central differencing, we will have it as f at I minus 1 comma j comma k minus 2 times of f at I comma j comma k plus f at I plus 1 comma j comma k divided by delta x square plus f at I comma j minus 1 comma k plus f at I comma j plus 1 comma k minus 2 times of f at I comma j comma k divided by delta y square plus f at I comma j comma k minus 1 minus 2 times of f at I comma j comma k plus f at I comma j comma k plus 1 divided by delta z square. So this is the equation we will be attaining. So here how many unknowns are there? We are having 7 unknowns actually. So the number of interior node points, leaving out the nodes next to the boundaries as well, will have 7 variables. So that is how many points? So interior alone, if we take, we need to subtract 2 more. So it is 39 points, 29 points and 24 points. So again we are subtracting 2 because we are taking only the interior. In the interior only we will be having full, that is 7 variables. So 39 minus 2, 29 minus 2, 24 minus 2, that will give 21,978. So these 21,978 will have 7 non-zero elements. So 7 non-zero elements. So it is 21,978 into 7 will give us 1,53,846 non-zero elements will be there. Now we are considering the layer next to the bottom and top wall. These will have one will go to boundary. So we will be having 7 minus 1. So I hope you are getting 7 minus 1 because 1 is occupied with the boundary. So how many points will be these? Grid points next to the top and bottom wall will be like 40 minus 1, 30 minus 1 into 6. So we are multiplying by 2 because we have top and bottom wall. So again it will give us 13,572. Similarly we can do for right and left walls and front and back walls as well. Grid points next to the left and right wall will have 6 non-zero elements. Similarly, we are doing 30 minus 3 because we have included it in the other sides, and 25 minus 1 into 6 into 2, 7,776. And grid points next to the front and back will have 6 non-zero elements. Again here we will be subtracting everything with 3 because we have included those things in the other equations. So 40 minus 3 into 25 minus 3 into 6 into 2, 9,768. Now we will be end up with corner points. Corner node points next to the boundary will have only 4 elements because it will give out 3 to the boundaries. So if we give out 3 to the boundaries, it will be like 7 minus 3. So it will have 4 non-zero elements. So how many corner points? We will be having 8 corner points. So it is corner node points are 8 and we will be having 32 non-zero elements from the corner node points. So calculations are actually approximate. There are certain points might be repeated, a certain point might have been left out. So that thing is there. Okay, coming back. Total number of non-zero elements in A therefore will be, we are adding up everything now, 1,53,846 plus 13,572 plus 7,776 plus 9,768 plus 32. It will give us 1,84,994. This is the total number of non-zero elements in A, and total number of elements in A will be like we got total number of equations as 27,144. So number of elements will be square of that. Since it is a square matrix, we will be having total number of elements as 27,144 into 27,144. So this is giving us this number, and percentage of non-zero elements in A will be like this divided by this into 100, which will give us 0.025 percentage. So it is percent of non-zero elements is this. So percentage of 0 will be 100 minus this. So it will be giving us 99.975. So it is in the question we can say clearly now. More than 99.9% of A will be 0. So that is how we got it. I hope it is clear now. So if you have any doubt, you can ask. Just look at it once. We will go to next problem shortly. So just to give you an idea, I'm just keeping it for a minute. So after that, we will go to next problem. Okay, now we will move to next problem. In question 10, what is asked? Which of the following statements is true about the SOR method if the coefficient matrix is diagonally dominant? So now we are into numerical methods, that is advanced scheme that week. So there are few statements regarding the SOR method, successive over relaxation method, and we are asked to find which of them are true. First one, its convergence rate increases monotonically with the SOR parameter omega. It is convergent if omega is between 0 and 2. And third one, its convergence rate is twice as much as that of Gauss-Seidel method. So options are option A 1, option B 2, option C 3, option D 1 and 3. So just take a minute and find out the answer. We will discuss it. Okay, there is one more option E, that is 2 and 3 also. We are asked to find the true statement. Okay, the answer is actually second one. B is the right answer. B2 is the right answer. We will see how. So first one, its convergence rate increases monotonically with the SOR parameter omega. Its convergence rate doesn't increase monotonically, rather it increases and then decreases. So it goes through that with omega. And it is convergent if it is between 0 and 2. So that is true. When it is between 0 and 2, it is convergent, and if it is not, its convergence rate is actually not twice as that of Gauss-Seidel. We need to find the optimal parameter of omega for it to be its convergence rate to be more than Gauss-Seidel method. So successive over relaxation, that is SOR method, as long as the omega is between 0 and 2, convergence is assured. That is true. The convergence rate of convergence is varying, which depends as before on the spectral radius of the new iteration matrix. Omega varies between 1 and 2 for the case of over relaxation, but the rate of convergence does not vary monotonically between 1 and 2. So that is false. And typically it goes through a minimum or the number of iterations needed to reduce a residual by a factor of 10. That value is asymptotically convergence rate. It reduces as omega is increased. It goes to a minimum and then it starts again coming back. So I mentioned it as increases and then decreases, but yeah, it is false. It decreases and then increases. So that means there is an optimum value of omega for a given matrix and for a given SOR method. So that is the case. Uh, Optimum value, if we find, we will be having convergence rate faster than Gauss-Seidel, but it is not twice as fast as Gauss-Seidel. So that is false. So that is for question 10. This optimum value will have the least number of iteration steps needed to reduce the residual by a factor of 10 and has the highest convergence rate. Now we are into question 11. In question 11, what is asked? Which of the following can be claimed as advantages of an unstructured grid method of solution over a structured grid solution? So we have an unstructured grid and we have a structured grid. Which of the following can be claimed as an advantage of the former? So first one, ease of tackling irregular geometries. Second one, ease of solution of Ax is equal to B after discretization. Third one, ease of grid refinement after solution. So we have 3 and option A it is 1 and 2. Option B it is 1 and 3. Option C it is 2 and 3. Option D 1, 2 and 3. So we are asked to find which of the following is advantage of unstructured grid over the structured grid solution. So yeah, find out, we will see. Okay, so the answer is actually, we will see statement by statement first. First one, unstructured grid uh, ease of tackling irregular geometries. So first one is true because getting a structured grid for irregular geometries is quite tricky. So when we use unstructured grid, we will be having ease of tackling irregular geometries. Second one, ease of solution of Ax is equal to B after discretization. This is actually false because unstructured grid getting a solution is very difficult, whereas you will the getting solution from structured grid is easier. That's why we prefer to have a structured grid in most cases, because if imagine if getting solution from an unstructured grid is easier, mesh generation is also easier with unstructured grid, then it would have been better option, right? But it is not, because getting a solution from an unstructured grid is very difficult. So second statement is false. Third one, ease of grid refinement after solution. So this is true. So in structured grid, what happens is that when you refine grid in one location, the other location will also be affected because of that. So in unstructured grid, that is not the case. You can refine it in one point without worrying about the mesh getting refined in some other corner. So that is an advantage of unstructured grid over a structured grid, which we will be seeing. So first one is true, second one is false, and third one is true. So answer is therefore option B, that is 1 and 3 is the right answer. So option B, 1 and 3 is the right answer. So that is for question 11. In question 12, we will have a problem from yesterday's class with the slide extension. Which of the following statements is true about Reynolds stresses? First one, they are not stresses per se but stress-like quantities. Second one, there are only 6 independent components in the Reynolds stress tensor. Third one, they are constant across the cross section of a pipe in a fully developed flow. So we are given three statements. First one is they are not stresses per se but stress-like quantities. Second one, there are only 6 independent components in the Reynolds stress tensor. Third one, they are constant across the cross section of a pipe in a fully developed flow. So we saw the problem in yesterday's class also, so it would be easy for you to recollect. I'll give you the options first. Option A it is 1. Option B it is 1 and 2. Option C it is 1 and 3. Option D it is 1, 2 and 3. Okay, answer is actually 1 and 2. First statement is true, second statement is true, third statement is false. So option B is the right answer. Option B 1 and 2. We will see why. So first one, they are not stresses per se but stress-like quantities. This is true statement. Reynolds stresses arise from the averaging process in the Navier-Stokes equations for turbulent flows. They represent the apparent stresses due to turbulent velocity fluctuations, not molecular interactions like true viscous stresses. They act like stresses in the equations, but they are statistical constructs and not actual physical stress tensors from intermolecular forces. So Reynolds stresses in the from the Navier-Stokes equations, they are apparent stresses due to turbulent velocity fluctuations, and they are not like molecular stresses which are arising from the intermolecular interactions. So it is not stress but stress like quantities. Second one, there are only 6 independent components in the Reynolds stress tensor. This is also true. Reynolds stress tensor is defined as a symmetric 3 cross 3 tensor that represents the correlation between fluctuating velocity components in a turbulent flow. In that actually 3 will be unique and 3 will be like symmetric values. So we will be having only 6 independent tensor components in the whole. So tensor is symmetric. It has 3 normal components and 3 independent shear components. So total 6 independent components. So second statement is also true. Third one, they are constant across the cross section of a pipe. in a fully developed flow. This is false. Reynolds stresses are not constant across the cross section of a pipe in a fully developed flow. In a fully developed turbulent pipe flow, Reynolds stresses vary with the radial position. Near the wall, the turbulent fluctuations are smaller, so Reynolds stresses are low. They reach a maximum at some distance from wall and then decrease towards the center line, so they are not constant across the cross section. So this is false. So that is the case. So that is it for today's class, and yeah, okay. Thank you for attending today's session. If you have any doubts, you can ask me. And again, thank you once again for attending all 12 weeks. And if you have any feedbacks to give to me, I'll be happy to take. Or if you have anything to discuss in particular, we can discuss that as well. And yeah, thank you so much for attending classes. And feel free to ask me questions and give your feedbacks as well. That will help me improve in my future classes. So yeah, thank you so much for attending today's session, and we will meet in some other thing in the future. mm, yeah, thank you so much. And yeah, it's 7:50 now. It is 6 p.m. today. Yeah. All right, I think people left, so I'll close the session. Thank you.